Hey everybody, Mr. Judson here. So today we're going to add two more functions to our list of basic functions that we know how to graph. We now know how to graph linear functions. We've actually known that for a long time, but we know how to graph parabolas easily, absolute values. We know how to do the square root and the greatest integer function. And there's only one more after these two, okay? So we're going to talk about the cubic and the cube root. Both very close to the same. There's just one slight difference between the two. So I think the first thing we want to do is we want to figure out, what does the parent function look like for this? If I was to graph the most basic function, y equals x cubed, what would that look like? And I'm not going to make an xy table this time. I'm going to try and make this go a little bit faster. So if I plug a 0 in here and I do 0 cubed, I get 0. So there's 1 point on this graph. If I plug in a 1, 1 cubed is 1. And if I plug in a 2, 2 cubed is 8. So we're way up here somewhere. So this graph is going like this. And it's going up fast, okay? It's going up really fast. If I go over to 3, 3 cubed is 27. So we're way up there, right? If I go in the negative direction, a negative 1 cubed, so a negative times a negative times a negative, that's an odd number of negative signs. That means my answer is negative. So I'm going to get, if I plug in a negative 1, I get negative 1. And so that would be this point right here. If I plug in a negative 2, negative 2 times a negative 2 times a negative 2, that would be negative 8. So again, we're way down here somewhere. And if I plug in a negative 3 cubed would be a negative 27. So way down, all right? So there's my parent function. And we've been kind of developing these rules like what's normal. And so what we see here is however far we go over in this direction from, this is our key point right here. We'll talk about that in a second. So n for any number, however many units I go this way, I have to go up n cubed. And if you think about it, we've always talked about, well, how many times more or less than what's normal are we going to do? And you can kind of start to figure this stuff out on your own. When this was a parabola, we had a 2 here, we did a times b squared. Well, now I'm going to do a times b cubed. All right? I don't really want to see a b value in there for this problem because, this can get big really fast. All right? But we got to follow those rules. So times ab cubed. This is how many times more or less we're going to go up than what's normal. What's normal is whatever this distance is, you do that cubed. Okay? And the same thing happens this direction. However far I go this way, I'm going down n cubed, and I'm multiplying that by the same thing. So a b cubed, this is how many times more or less I need to do than what's normal. Okay? So, this point right here is I guess our key point for this graph. It's that one special point that we always talk about. And we're going to refer to that as the point of inflection. Okay? It's actually a calculus word. It's where the curvature of the graph changes. So, imagine if you're driving along a road, you're turning off to the right a little bit, and you turn into the right, and then also you get this point where we kind of straighten the wheel and then begin to turn back to the left. That's that point where the curvature changes. And for us, that's a key point on this graph, and it's going to be at negative c over b comma d. That one key point that we're always looking for. Here it's that turning point, the point of inflection. Sometimes I'll abbreviate this POI for point of inflection. Okay? So really that's everything. I think all the things that we have talked about before, if A is negative, it's going to flip my graph across the x-axis. Really important that we kind of get those words in our head. Flip across the x-axis, okay? Not just flip it over. We're actually taking this, we're taking this stuff, we're flipping it to the other side of the x-axis, we're taking this and we're flipping it to the other side of the x-axis, okay? And you'll see later on why those words are important, that we want to get the x-axis in there, okay? If B is negative, then I flip it across the y-axis. This piece goes over here, this piece goes over here. So you kind of think about that and think, if A or B is negative, they both really look the same. You know, it's going to look like this. Let me just draw something in here. What color can I choose? If A is negative, it looks like this. I'm going to take this back out in a minute. Or if B is negative, it looks like this, right? Because if this piece flips down here, or it flips over here, doesn't matter, it looks the same, okay? The transformation isn't the same, but it looks the same at the end. All right, so let me take that out of there. All right, cube root. You're going to see that it's very similar to this, just one slight difference. So let me set up a graph here. First of all, my most basic function is going to be y equals the cube root of x. All right, so and again, I'm just going to start plugging numbers into my head. I'm not going to write them down. I'm not going to make that xy table. I'm going to think if I put a 0 in here, the cube root of 0, what number times itself 3 times equals 0? Well, that's 0. So I would get 0, comma 0, this point right here. What's the next number I know the cube root of? 1, right? What number times itself 3 times equals 1? That would be 1. Okay, so I get the point 1, comma 1. But then when I ask myself, what's the next number I know the cube root of? It's 8. Right? The cube root of 8, which means what number times itself 3 times equals 8? That'd be 2 times 2 times 2. So I have to go all the way out to 8, which is way out here somewhere, and then up 2, and I get another point. So this graph is looking like this. It's almost like a square root, but a little bit different. Now what about if we go this way? Can we do the cube root of a negative number? Yeah, we can. The cube root of a negative 1. What number times itself 3 times equals a negative 1? Well, a negative 1 times a negative 1 times a negative 1. That equals negative 1, right? So the cube root of negative 1 is negative 1. The next number that I would know the cube root of is going to be way out here at negative 8. So I'm going to come all the way out to here, to negative 8. The cube root of that is negative 2. So I have a point way out here somewhere. And so this graph is going to look like that. It's a sideways version of this graph. That's why we can do both of these at the same time. So the important thing to remember is the cubic function stretches up and down. The cube root stretches to the left and to the right. That's the thing that's really important to remember. Okay? This point right here is still called a point of inflection. If we ask ourselves what's normal is however far we go this direction, we have to go up the cube root of that. So the cube root of n. Oops. Okay, the cube root of n. And same thing this direction. However far I go this way, in the negative direction, I'm going to go down the cube root of that distance. Okay, that's what's normal. Now we always got to ask that question, well, how many times more or less than what's normal are we going to stretch this thing? And so I need to multiply this by a times the cube root of b. A cube root b. Same thing over here. Times, I don't have room to write this, but a cube root b. Okay? Now, you can think about that, and that can get pretty messy. I want to be really careful when I write an equation that when you do this whole thing, we're not getting some ugly decimal number that's difficult to work with. I mean, I could, if I had to, if I work this all out and I get something like 1.8, whatever comes afterwards, I don't really care after that, I just want to keep it simple, well, I'd have to do 1.8 times as much. I'd have to grab my calculator and say, if I go over 8 units, I should go down 2, so what's 2 times 1.8? Figure that out, and that's how far down I'm going to go. Okay, I could do that. The rules work for decimal numbers, it's just we want to try and keep it easy. Okay? So let's see. We know how to find our points of inflection. It's still negative c over b comma d. That's always going to be the first thing we look for. We now know what's normal for both of these. And we know how to figure out how much more or less than what's normal. So we just need to try a problem here. Okay? Let's try one. All right, so we'll do one of these together, and then I'll let you guys try one. So when I look at this, first thing I see is a cubic function. So I know what that looks like. It goes like this. But it's going to get flipped across the y-axis. So when I flip that over, my function now looks like this. Okay, so that's the picture I want to draw. I just want to get it straight in my head what the graph is supposed to look like. Okay, so now my point of inflection, that's my key point, is at negative c over b. So 3 divided by negative 1, that'll be a negative 3, comma 1. So I know where that point of inflection is at, I know what the graph looks like. I just need to decide more or less than what's normal. So if I do a times b cubed, that's going to be 1/2 times, I don't care about the negative signs right now. I already know what that does. It flips it across the y-axis. So I'm just thinking my b value is a 1 cubed, then 1 times 1/2 is 1/2. So I'm going to do half as much as what's normal. All right, so let's draw a sketch of what this graph looks like. All right, so point of inflection is at negative 3 comma 1, right here. I know the graph looks like this. It's going to come down, go through that point, and do this. If nothing else, at least draw that picture. You've got most of the credit for this problem, all right? But we want to try and get some points in the right spot. So this part that curves down, if I go over 1 unit, 1 cubed is 1, so I want to go half as far. If I go over 2 units, 2 cubed is 8, but I want to do half of that. So 1, 2, 3, 4, right there. If I go over 3 units, 3 cubed is 27, half of that would be 13.5. That's too far. It's taking me off the grid here. So let's go the other way. If I go over 1 unit, 1 cubed is 1, but I'm going to do half of that. If I go over 2 units, 2 cubed is 8. Half of that would be 4, so 1, 2, 3, 4. And now I just have to draw that curve in there. And this is really important. Remember, don't go past the points that you've plotted. Okay? There's no reason to keep on going down. I just want to start right here, do this, and then stop. Okay? I mean, I am going past it a little bit, but don't extend your graph way beyond that. Because usually what happens is we start to do things that shouldn't happen. Here's something else that's real important. Let me back up and do this again. I see this happen a lot of times where people go like this, and they go, oh, whoops, went too far. Oh, well, there we go. That's a problem because that doesn't pass the vertical line test, right? If this was on a test, I would go like this. I would go VLT, vertical line test, minus 1/2. There's that half point thing again, right? People get tired of half points, but it's because we got a little careless right here, right? We know that a vertical line should only hit a graph once. Now, let me just back up and do this again. If I draw this graph, is Judson going to go, oh, it looks like you hit 2 points on a vertical line there? No, I'm not going to do that because I know that this thing starts to go up pretty fast and it goes down pretty fast. It's when you go beyond this point and then come back to hit it. That's when it becomes an issue. Okay, so we just want to think about that as we're graphing. All right, let me get you guys one to try. All right, you guys go ahead and try this one. So one of the first things that I see here again is I don't like the way this is written. Somebody's trying to mess with me. All right. So I always like to see the x term first. So I'm just going to rewrite this: a negative 1/8 times a negative 2x plus 4 cubed minus 3. Now I've got my a, b, c, and d values. Okay. So I'm going to flip this across the x-axis, and then I'm going to flip it across the y-axis. And so what it means is we're back to what the original function looked like. Okay, the parent function. Once this flips down and then it flips over, it's kind of like these two curves are just trading places, but it looks the same. And then I need to have my point of inflection. That's going to be at negative 4 divided by a negative 2. That'd be a positive 2, comma negative 3. And then what I have, if I do my a times b cubed, I've got 1/8 times 2 cubed. Remember, I'm ignoring the negative signs when I deal with this. I'm just trying to find out how much more or less than normal are we going to adjust our y values for this graph. So if I cube this first, I get 8. 1/8 times 8, that would just be 8 over 8, which is 1. So that means this is a normal cubic function. Right? It looks like the parent function, even though we got two negative signs. Even though I got a fraction and another number, it's just a normal cubic function. So I can go ahead and draw that picture now. My point of inflection is at 2 comma negative 3. It's right here. And so then if I go over 1, 1 cubed is 1. If I go over 2, 2 cubed is 8. I could actually fit that in this way. 1, 2, 3, 4, 5, 6, 7, 8. And if I go this way 1 unit, 1 cubed is 1. If I go over 2, 2 cubed is 8. It's going to take me off the screen. So I want you guys to see something here. Had I not put that point in, it's a real common mistake for people to draw this graph like this. And see, even though that's pretty close, it's really off because we're saying if you go over 2 units, I should hit this point, which is up only 2 units. I am curving, but it's not curving up as fast as it should. I should be hitting this. So really the key to this is when you draw this graph, after you go through this point, make sure you don't cross this next column of dots unless you do it right here. Okay? Honestly, I probably wouldn't even do that. I would just go ahead and draw the graph here, but I don't want to go past the next column of dots as I draw this. See how I'm kind of staying right in between those 2 columns of dots? That's a pretty good graph right there. You draw it like that, you're going to get it right every time. Okay? All right, let's try a cube root function. So we know this is the same as the cubic function, it's just that it's going to extend left and right instead of up and down. Okay? You guys go ahead and try this. All right, so I'm not flipping across the x-axis and I'm not flipping across the y-axis. So this graph should look like this. My point of inflection is going to be at opposite of this, so a positive 24 divided by 8, that's 3, comma 4. And a times the cube root of b, this is going to equal 1/4 times the cube root of 8. So cube root of 8 is 2. 2 times 1/4, that's 2/4, which is 1/2. So we're going to go up half as much as what's normal. When you go way out sideways, you're already not going up very far. You know, now we're going up even less, which makes it kind of harder to see these curves in there. But that's okay. We'll follow the rules. We'll do what it says. So 3 comma 4, right there. I know the graph looks like this. And so if I go 1 unit out, the cube root of that is 1, but I'm going to do half as much. And I would have to go out 8 units. The cube root of that would be 2, and half of that would be 1. So I want to make sure I don't cross that next row of dots. I don't want to go above that unless I do it way out here somewhere. Okay? And if I go the other direction, 1 unit, the cube root of that's 1. I'm going to do half as much. If I go out 8 units, 1, 2, 3, 4, 5, 6, 7, 8, the cube root of that's 2, but I'm only going half as far. So when I draw this part down here, I don't want to cross this row of dots until I get to that point. Okay? Now again, I would choose not even to include this point in the graph. I would just draw something like this. And real important that we see this. Had I drawn something like this, see, I'm crossing this row of dots in a spot where I shouldn't, so I'm off by just a little bit. I would look at that and go, that's not bad. You knew what the graph looked like. You got the point of inflection in the right spot. General shape is good. We just missed a point that we should have hit. Okay? So I want to be real careful with those additional points in here. And honestly, I think if you really understand what you're doing, if that's our goal, is to really make sure I get it and understand, it's not very hard to make sure that graph looks right. Okay? As long as I understand that however far I go out, I'm doing the cube root of that distance, but then cutting it in half, it's pretty easy to get this right. Okay? We do have to understand the rules though. All right. I'm going to go back and erase this point because I don't really want that to be part of my graph. Let's try one more. All right, so this time I've got y equals a -2 times the cube root of 1 minus x, and then -1 on the outside. You guys go ahead and try this. All right, so again, I don't like the way it's written. I want to fix this. I've got -2 times the cube root of, I want to see the x first, and the 1's positive, and then -1. Now again, you don't have to write it like this. If people can look at this and keep everything straight in their head, that's fine. But trust me, after doing this for so many years, I see a lot of mistakes. The more you try to do in your head, the more mistakes we make. Which, of course, then you go, well then, geez, Judson, why are you showing us all these shortcuts? Well, we do like to shorten things up, right? We don't do multiplication of 3-digit numbers where we write the whole thing out and keep track of the columns and slide things over. We don't do that anymore, right? We just do it on the calculator. That's a shortcut. So we want to take shortcuts even though we know how to do things. I want to feel really comfortable first with the fact that I know what I'm doing, and then start pursuing the shortcuts. All right, so we're flipping across the x-axis first, and then taking that and flipping across the y-axis, which means my graph is going to come back to what the parent function would look like. And again, what's really happening is the two curves on either side of that point of inflection, they're really just switching spots when both of these are negative. All right? All right, point of inflection, that's at -1 divided by a -1, which is a +1, comma -1. So if I draw the graph, there you go, and I plot that point of inflection, 1 comma -1 is right there. Okay. Now I do have to pay attention to how many times more or less than normal. So a times the cube root of b is going to equal 2 times the cube root of 1. So you got to do the cube root first. That's 1 times 2, that's 2. So we're doing twice as much as what's normal. That's pretty easy to work with. So if I go 1 unit over, cube root of that's 1, but I need to go twice as far to 2. If I go out 8 units, cube root of 8 is 2, but I'm going to go twice as far to 4. I'm going to go ahead and plot that point. 1, 2, 3, 4, 5, 6, 7, 8. And then I want to go up 4 from that. Cube root of 8 is 2, but twice as far would be 4. So 1, 2, 3, 4, right about there. So you can see here, it is okay to cross that next row of dots. I'm not sure exactly where, but I don't want to cross the next row after that until I get to that point. Okay? If I go this way 1 unit, the cube root of that's 1, but I got to double it. And if I go out 1, 2, 3, 4, 5, 6, 7, 8, cube root of that's 2. If I double it, I get 4. So I'm right about there. Now again, you don't have to go get these points way out there, but you can if you want. Just to at least help you see where this graph is supposed to go. And so then if you do this, even if you stop right there, I'm okay with that. You can even go back if you want and erase these points. I think I got a pretty good picture. And if I do something like I take off points here, you would just say to me, well, Judson, if I go out 8 units, the cube root of that's 2, and if I double it, I get 4, that arrow's pointing right at where that point should go. Shouldn't I get that right? And I would go, yeah, you should. Oops, my mistake, you know. So yeah, I'd have to fix that, because this would be correct. All right, that's what we have for today. Let me get you guys a homework assignment. All right, so here we go. This would be our next worksheet. You can go ahead and snap a picture of it right now, if you'd like, or again, I will have this on the classroom website. Again, I'm still mixing in things like parabolas, an absolute value, here's a greatest integer function, there's a square root function. So we want to make sure we keep on practicing all of these so that we don't forget. Okay? Here's what's going to happen. We talked about our next test. I can't put all of these functions on each test, right? I mean, by the time we're done, there's like 8 or 9 of them. I can't ask you guys to graph all of those. It'll take too long. So what I'm going to do is I'm going to pick maybe 2 to put on your test. You just don't know which 2 I'm going to pick, all right? So we have to make sure we know all of them. And the 2 that I picked for one class, I might pick a different 2 for another class, all right? So anyway, you know, real important to go back and review those and make sure we have them all straight, okay? All right, that's it. That's all I have for you guys for today. So have a good weekend. Take care. Be safe. See you next week.